Hi there, I'm Stefan T. Lauwade, and I am a Visual C++ Libraries developer. Specifically, I maintain Microsoft's implementation of the C++ standard library. We licensed it from a third-party company called Dinkomware, who originally implemented it and still maintains it. I work on Microsoft's side with them to fix bugs. I reply to customer bugs. I work on things like our visualizers. And today, I'm here, based on feedback from people who've watched my previous Channel 9 videos, to talk about the standard library, and specifically the subset that we call the STL, the standard template library. So C++ is a very advanced language, and one of the reasons why it has so much complexity is to permit the creation of very powerful and easy-to-use libraries. If you look at really every feature in the core language, which is the part of the language that you get when you don't include any headers, virtually every one of those features exists to permit some aspect of a library. If you look at virtual functions or templates, they're handy by themselves, but they're really powerful when they're powering a library that has a simple interface that people can use to access code written by someone else. So the standard library is the library that comes with every copy of a compiler. And it has a long history. The part that I'm talking about was originally developed around 1994 or so, and has evolved very rapidly since then, particularly with the new C++ standard being developed called C++ OX. And there are other libraries that work well with it, open source libraries like Boost, things like that. But if you use a big library, learning it is almost like learning a sort of mini language. And many programmers use C++ all the time, but they haven't used the standard library and the STL extensively. It seems somewhat unfamiliar to them. But the great thing is, if you're already using C++, you already have the standard library. It's right there, ready for you to use. So today I'll be talking about the high-level overview of the standard library. I'll go in, show some examples of using it. I'll try to touch on a few more advanced topics, but I really want to start at the beginning and explain sort of the mental models behind this thing, because it really is unlike any other library you've seen before, except for the libraries that follow its principles, like Boost. So the most important point I want to explain is point 0. There are books. Because the standard library has a very long history, many people have written books about it, and even in today's modern age where we Twitter and Facebook and chat on social networking to learn things, to learn something in depth, nothing really beats reading a book cover to cover as a tutorial and then going back and referring to it as a reference. So there's many C++ books. I can't possibly enumerate all of them. My favorites for the standard library are the C++ Standard Library, a tutorial and reference by Nikolai Jasudis, and Effective STL by Scott Myers. Jasudis' book is exactly what it says on the cover. It explains the STL, and in fact, the whole standard library from scratch, whereas Effective STL is what I call a morality guide that assumes that you're familiar with using the STL at an intermediate level, but it explains traps and pitfalls, gotchas, ways to use it more effectively. And there's many other books that go into customizing the STL. Eventually, there will be books about the C++ OX features. There's already a book about the TR1 extensions to the standard library. Many resources out there. So because there are books, I won't go into extreme detail about all the member functions of the containers I'm talking about. The standard library has over 100 algorithms. I won't mention every one by name. I think that what I can contribute is a high-level overview of what the STL's components are, why it's structured the way it is, and guidance, like what kind of container should you be using. The first time you use a library, you're sort of overwhelmed by all the different features that are available, the fact that you have to choose what to use. And the STL, because it is the main library for C++, offers incredible power, advanced power. But you have to learn how to navigate it. So I think explaining some of that will help you read books and understand them a little more effectively. The other point I wanted to make, point 1, is that the STL, the standard template library, is a library, not a framework. So the difference is that a framework says, here is a huge chunk of code. You can write applications by writing a little bit of code and plugging it into it. Power the UI model or whatever it is. Whereas a library says, I'm a chunk of reusable code, but I expect you, the end user programmer, to use me, the library, in whatever application you're using. So a font library allows you to go read a font and process an outline. A networking library allows you to talk to the network, but it is very much a servant, and you are the master when it comes to writing code. What that means is that if you're using a library like the STL, you can use as much or as little of it as you need. You don't have to completely convert your code over to using it. In fact, the STL works very well with algorithms that don't know anything about it, like plain old C APIs. It can talk raw pointers if necessary. And I'll demonstrate how to use that. Now, unlike libraries like font libraries and networking libraries, the STL is a library for general computation, or pure computation, as I sometimes call it. What that means is that it's not focused on any particular thing. It doesn't care about fonts, doesn't care about networking, doesn't care about graphics. It doesn't care about whatever your program is doing. So why would you want to use it? Well, it cares deeply about things like performance and correctness. It has things that allow any program to benefit. Every program needs to talk about sequences of things. It needs to perform sorting. It needs to perform searching. I read somewhere that if you look at what programs do, 90% of it is sorting and searching in different ways. The STL is great at that. So it can really be used in almost any application, from something that is embedded to something that's running on a server to running on a desktop. The STL is available everywhere that C++ is available. Really, the only thing that gives it trouble is kernel mode. But as long as you're in user space, you should be able to use the STL if you are using exception handling as well, which is part of the language. So how do we start with the STL? One of the things that is very famous about it is that it has this sort of unusual structure. And it's got really three chunks that authors of books will talk about. It has containers, iterators, and algorithms. And they talk to each other like this. There's actually other parts of the STL that are involved here. For example, function objects or functors can be used to customize algorithms. They can also customize containers. And this is just an overall structure. So there's actually nothing stopping you from writing your own containers, your own iterators, your own algorithms, and your own function objects that work with the STL. So if you write your own container or get one from a library like Boost, you can use it with existing STL algorithms. Or you can write your own algorithm and use it with existing STL containers. And there's a method behind this structure. Back before the STL was first developed by Alexander Stepanov, many people had libraries while C++ was being developed for general computation. Things like doubly linked lists, flexible arrays. And the problem was they ran into this issue that's now called the n times m problem. If you have n containers like flexible arrays and doubly linked lists and singly linked lists, and m algorithms like a sorting, a replacement, a removal, and they're all member functions of the containers, then you have to write n times m implementations of those algorithms. That's actually really obnoxious, hard to maintain, and difficult to learn. So what Alexander Stepanov did when he developed the STL is said, I can actually break this out and prevent these components from knowing so much about each other. So that's why there are these iterators here. Containers return iterators, which are ways to talk about the individual elements of a container. Containers don't directly talk to algorithms. Instead, algorithms operate on the iterators of a container. And thanks to templates, which is the feature that the STL uses extensively, the algorithms, we can have a single algorithm that's templated on an iterator type, and that therefore can work with any container that meets its requirements. So we end up writing n container implementations that don't know anything about algorithms, m algorithm implementations that don't know anything about containers, and they can actually work together. And the great thing about the STL is because it's using templates, when they get instantiated by the compiler, everything is inlineable. You're not paying any virtual call overheads, and virtual calls inhibit inlining. That's the other thing that libraries before the STL tried to do. They tried to get generality by using inheritance and virtual calls. And that's very good for some applications, but it's not good when you're looping over 1 million elements and every single cycle counts. The STL cares extremely deeply about performance. And its goal really is to have equal or even superior performance to handwritten C code. Now that sounds impossible. How could you possibly be faster than handwritten C code? And it is true that because C is Turing complete, a dedicated, tuned, highly customized implementation can always beat any general library. But the thing about the STL is that it is maintained by people with decades of experience who know what they're doing, who are paid to sit around all day thinking about how to get the most efficient implementation of algorithms and containers. So by using the STL, you are using all of that work that has been put into it. Whatever you're doing, whether it's networking or graphics or a server application, you don't have time to spend figuring out the most efficient search, the most efficient implementation of a container. You can learn new features like C++OX's R-value references, but you just don't have time to go apply them to existing container implementations. We, the maintainers of the standard library, we do have time to do that. So by using the standard library, you can focus on whatever it is that makes your program great, whatever it's doing. So that's sort of a high-level overview of the standard library. Now the containers are sort of the most popular. They're the stars of the standard library because they contain elements. Elements are anything. So here I've got a little bit of code that's sort of the hello world of the STL. This program actually does nothing. It has a vector of int. So vector is sort of the workhorse of the STL. It is a sequence container. And what a sequence container does is it stores a sequence of elements. So if I have a vector of int, it's storing a sequence of integers. Maybe I'm thinking that it stores 11, 22, 33, and 44. Now the STL doesn't care about what those elements are. They can be ints, they can be strings, they can be your classes. They just have to satisfy certain requirements. In particular, the elements of an STL container have to behave as values. They have to be copyable. So as long as your class is copyable, it can be used, and assignable, it can be used in the STL. Beginning in Visual Studio 2010, VC10, the STL can also work with movable-only types like unique pointer. That's relatively advanced. As long as your types are copyable, they will definitely work with the STL. So in my examples, I'll be using int because it's simple. I don't have time and you don't want to see me write a whole huge example that's more realistic. So it's somewhat abstract, but wherever you see int, you can think, oh, I could put my own type there. The STL even works with containers of containers because a vector int is itself copyable. So I could write a vector of vector int like this. And now essentially I have a two-dimensional container that can store one container of subcontainers like this. And this is actually surprisingly efficient thanks to various optimizations we have in there. In particular, if anyone tried to write this by hand, it would be massively slower because it would involve a lot of redundant copying. And the STL simply makes it extremely efficient. So sequence containers care about the order of elements that I put them in. So let me go back to my single-dimensional vector, which is sort of the most common type of vector. I can insert elements in it by pushing them back. So when I default construct a container, here if I say vector int v, I'm default constructing it. What this means is that it's initialized to be empty. So if I'm thinking about what the container looks like, I've got my vector v, and it simply contains no elements. So there's no elements here. Now, I'll be sketching out the representations of STL containers because it's always very useful to have a mental model of what the thing looks like. Now, of course, you shouldn't necessarily need to know all of the underlying implementation details. I'll be glossing over all of that. In fact, there's dangers to knowing too much about the implementation, because what if it changes? You should only assume what's guaranteed by the international standard for C++. But the way that a vector works, its implementation at a high level is really mandated by the standard. It's got to be a flexible array that's contiguous, that sort of thing. So I can start inserting more elements at the back of a vector by saying v pushback. Here I'm getting some IntelliSense that shows me what the signature is. I don't use IntelliSense, so I'm just going to ignore that. And I can push back 11, and then a little more, v pushback 22, and so forth. So when I push back an 11, what that means is that my vector gains an element, 11. And then if I push back a 22, I get another element, so forth. Because it's a sequence container, it's storing the sequence that I push the elements in. Very often it matters what order things are in. Then I can run algorithms on this. I'm just simply showing the basics of the container. Now, the thing about the STL is it cares deeply about performance. Vector is a flexible array. And what that means is that its elements are actually contiguous. These are guaranteed to be packed together in memory as if you had a built-in C array, or if you newed up something with new bracket bracket. Processors love contiguous elements. If you look at their caching structure, they just love blasting through memory, incrementing whatever address it is. It's also space efficient, because you're not spending any extra dynamic memory allocations, that sort of thing. However, if you look at, say, a contiguous chunk of memory, maybe the vector is allocated space for 3 elements. Well, what happens if I go and push back a 44? I need a new memory block. So vector will reallocate. So say the vectors has space for 3 elements. I push back another. What will happen is we'll reallocate more elements, copy the existing ones over, and then insert the new element that you just pushed back, say the 44, and then it will get rid of the old memory block. I'm not showing exactly how many elements the vector has allocated here, because it varies from implementation to implementation. The key thing about this is because vector cares about performance, what it does is exponential or geometric reallocation. So if you start off by storing n elements and it has to reallocate, what the vector will do is it will store n times some factor k. The factor k has to be greater than 1. In our implementation, Visual Studio's implementation, we currently use a factor of 1.5, which we think balances various performance trade-offs. Other implementations use the factor k equals 2, so the vector's capacity will constantly double. Other factors k are possible, but 1.5 and 2 are the most common. Now, what this does is it provides a very important performance guarantee, and that's when I push back a new element. So if I have a vector of some huge number of elements, 100,000, a million, the STL has no problem with that, and I push back a single element, what the STL guarantees is that the time that it takes to push back that single element is amortized constant time. This is a term from computer science theory. If you haven't heard of it, what amortized constant time means is that any individual pushback may trigger this reallocation, and when I have to go copy all of the existing elements, that will take linear time, linear in the number of elements that I have to go copy. But because reallocation happens so infrequently, if you do all the math, for any individual pushback, it takes an average of constant time. This is extremely good for performance. Now, if you look at handwritten containers, unfortunately I've seen many in code that really should be using the standard library. One popular thing to do is to reallocate some fixed number. For some reason, programmers like to choose k equals 10. Oh, I'll just reallocate 10 more elements. That seems like a good chunk. Now, at first glance, that might seem to be space efficient, because you'll never be paying more than 9 empty elements in memory that are waiting to be filled. Unfortunately, if you do the math, as you're pushing back elements, and if you're reallocating a constant number more, what will happen is that the time to push back n elements actually takes time proportional to the square of the elements that you push back. So if you push back 1,000 elements, the time to take that would be proportional to 1,000 squared. That blows up, in terms of time, horribly. Quadratic performance is really a killer. If it's unavoidable, then so be it. But for most applications, you really want linear performance or better, or n log n. The STL guarantees that you will not get quadratic performance. Instead, if you're calling pushback, you'll get linear time performance, and this factor will go away. So that's just one of the many ways that the STL helps, just sort of behind the scenes. If you're looking at the use of a vector, vector in V pushback, you don't see any of that. The vector is performing the dynamic reallocation for you. The other thing about the STL is because its containers are flexible, this prevents security problems and correctness problems like buffer overflows. Every STL container knows its own size, so I can ask the vector, hey, what's your size after this? I can print v size, and it will know its own size. I can execute this. Build succeeded. And if I look at the program, it has printed out that the size is 2. Actually, that's a very small font, but that's saying 2. So this is unlike built-in C arrays, where if I have an array, like int array r of 5 is blah, 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 and I pass this array to some function, that will be passed as a simple int star. A pointer to a bunch of ints doesn't know how big it is, so you constantly have to be passing the array size around. If you get the size wrong, or there's macros to automatically figure out the size of an array. But if you ever index beyond the end, then you'll go potentially corrupt memory. You've got a security problem. The other problem about, and this is a really lethal problem about built-in C arrays, is that they have a fixed size. If I say int r5, then that array can hold only 5 elements and no more forever and ever. So what if I ever need 6 elements? What if I'm a program talking to the network and an attacker who's claiming to be an ordinary user gives me 6 elements? What if I don't have the proper check there to say, oh wait, I only want 5 elements, and I happily scribble off past the end of my array? Well, then I've got a problem. I've got a security problem. This sort of buffer overflow, buffer underflow, heap overflow, that sort of thing is extremely lethal. There are all sorts of ways to mitigate the problem, checking, testing, secure functions, but the underlying problem is best avoided in the first place. If you look at STL containers, they're flexible. They can store arbitrary number of elements. The STL is big on this word arbitrary. It can store arbitrary numbers of arbitrary elements. It doesn't care what the elements are. It doesn't care what you do with them. As long as you observe certain rules, you'll be just automatically protected from the problems that plague C and C++ programming without the STL. So one of the things that you have to be aware is that in order to flexibly grow a container, you need to be using functions that say that they're inserting new elements. What the STL will not do is automatically insert new elements into a vector. So if I've got, say, let me push back one more element, push back 33, I can iterate through this vector. I can say for, and to be proper, I'll include the right header for this, std def.h, and then I'll collapse this so it doesn't take up space. If I say for size t, I is 0, I less than v size, the vector knows its own size. This is great. And then I can increment I if I print. Here I'm just using IOStream cout. This is not part of the standard template library proper. It's part of the C++ standard library. You could also use a printf here. The STL really doesn't care. Of course, cout is at least type safe. I could say v of I and now and print this out. If I execute this, build started, build succeeded, and I look at what it printed, it will print out 11, 22, 33, exactly as I hoped. Now, if I had said something here like v of 5 is 55, this is an error. Here I'm simply telling the vector, hey, access your 5th element, but at this point it only has 3 elements. So what will happen is I've got my vector here, v, that is pointing to block elements like this, 11, 22, 33. Maybe it has space here for some elements, maybe not. I haven't looked at the capacity. But if I ask it to access its 5th element, it's going to be looking at an element that doesn't exist. This triggers what the standard calls undefined behavior, meaning that the standard does not place any requirements on a compiler and library, like Visual Studio, as to what happens. That means that it could crash. It could work silently and then crash on your user's computer. It could send an email to your boss telling him you quit. It can format your hard drive. Anything could happen, or worst of all, it could do exactly what you expect until 2 years down the road where it actually does break. So you should not trigger undefined behavior. Now, with Visual Studio's implementation, when you compile in debug mode, we have checks beginning in 2005 and above, and enhanced in every version since then, that will detect common cases of misusing the STL and will pop up handy assert dialogues. So I believe I'm compiling in debug mode here. If I actually execute this, I'll recompile and run it. Come on, start. Here we go. I will get assertion dialog. Now, one of the things about this is it's somewhat confusing, somewhat misleading. We'll be looking at enhancing this in future versions. But what it's really saying is that there's a bug in your code, you being the user of the STL and not the STL itself. It's misleading because this dialog begins with the title Microsoft Visual C++ Debug Library and says debug assertion failed, which kind of sounds like it's detected a bug in the STL. In fact, it's detected a bug in your code. And what it's actually doing is it's pointing out where the thing exploded. Unfortunately, it only knows where it exploded inside the STL itself, so it'll be pointing to an include file in the vector header itself and a line there. But if you look at what that line is doing, and if you look at the expression that's going on here, it says expression, vector subscript out of range. This is fantastic. This tells me exactly what's wrong with my program. I used a subscript of a vector, and it was out of the range of the vector. Because this vector only has 3 elements, I can only use indices 0, 1, and 2. So if you pay attention to these debug assertion dialogues, they will actually tell you exactly what's wrong with your program. Now, of course, you should write your programs correct in the first place to avoid these entirely. But if you see one of these, you'll know what it means. Now, we turn off all of these debug checks in release mode so that we're not spending time with the conditional branching and validated programs that should be correct. But in debug mode, you will get these, and they're wonderful. So I'll just abort that and kill it. So if I want to insert elements, I need to be sure that they're there. I can't simply say, refer to the 5th element of a vector and hope that it's there. I need to be guaranteed that it's there. So I could push back a 44 and a 55, and then my vector would be flexible and have that number of elements. Now, if you look at what the STL is doing, here I've got a vector of int. That's how I pronounce it, vector of int. Sometimes I'll just skip that of in there. It's a template, so I've got these angle brackets here. It's templated on the element type, so I could easily have a vector of string. I'd have to go include the header for string. Here I actually haven't done that. I would need to do that. And then I've got a vector of string. Or I could put a vector of long, whatever I want here. So because it's templated on its element type, whenever it's instantiated, it just automatically knows how to insert elements of that type. It's also using operator overloading. If you look at vector, it's a class type. It goes class vector, and it's got member functions like pushback. It's overloading operators in order to imitate a C array. So when I say the bracket 5 bracket, that's calling operator bracket bracket, which is a member function of vector that goes and finds the nth element and returns a reference to you. So because the vector is using operator overloading, it's just more natural to use. You know how to use C arrays, so you know how to use a vector. You do need to learn things like pushback and the fact that it's reallocating, but its ordinary usage looks very much like a C array. Now, the STL doesn't try to imitate built-in arrays too extensively. It goes so far and then no further. But that principle that when possible imitate C and C++, the core language, is present throughout the STL. So here I've showed how to use pushback and get some elements. You'll notice that, of course, vectors are 0-based. So if I've got elements 11, 22, 33, these begin at indices 0, 1, and 2. Here the vector size, I'll erase this arrow. The vector size is 3. This is just like a C array. If I had an array whose size was 3, I would be able to access elements 0, 1, and 2, and I would not be able to access element 3. 0-based indexing is wonderful, and the STL uses it. I can also use what are called iterators. Here I've used indices just to avoid showing iterators. Now I'll actually use iterators. Let me go back to a vector of int. Let me erase this statement that will kill the program. Here I've got a V clear at the end that I've put a breakpoint on just so I can stop the program before it ends because I'm running it from the IDE. You can ignore that. So if I want to use iterators, what's an iterator? Well, I've got my vector here. If I get an iterator I can have that iterator point to an element of the vector, like 22. So here I could say, delete this, I could say vector int, and I need to get its nested type iterator, I, and I'm going to get an iterator to this element here, and I can do that by saying vBegin plus 1. And then I can print out whatever the element is. This is highly unrealistic. I would have no reason to do this in an actual program. Get an iterator to a single element and then print it out. But I can show what it looks like. Build started, succeeded, and I get printed out 22, which is element at index number 1. So when I request, minimize this, when I request vBegin, what I get is an iterator to the beginning of the vector. So this is the vector's beginning here. Then if I add 1 to it, I'll get an iterator to the element past that. So this is begin plus 1. This is what my iterator I was, and then when I dereferenced it and printed it out, I got that element. I can use this to iterate through a vector. This is much more common. So I can say for vector int iterator I is vBegin, I not equal, I've got this, oh, my program is still running. Let's kill that. The end plus I. I'm writing this in a certain form. I can print out whatever is there. And compile, run, and now I've printed out every element of the vector. So what this is doing is, let me kill it again, it's getting an iterator to the beginning of the vector and printing out that element, stepping it forward, printing out that element, and so forth. And then when it hits the end, it stops. So this is one of the things that initially confuses programmers when they first start using the STL. And that's that the end iterator, I'll just erase this begin plus 1 here, points to 1 past the end. So if I get a iterator to the end of the vector, if I call v.end, and I try to look at the element that's there, that's invalid. I'll crash the program with one of those debug assertion dialogues in debug mode. And this is what's called inclusive-exclusive ranges. The way that I write this down is if I have 2 iterators, x and y, the range of elements that I refer to, I write that like this, x, y, and then a parenthesis. So the square bracket here means inclusive. I include the element that the first iterator is pointing to, and the parenthesis here means exclusive. I'm not including the element at the end. So the range begin, end, like this, begin. When I write this down, this is not C++, it's just a notation you'll see in books, refers to all the elements of the vector, but not including this location at the end that does not actually contain an element. So this seems confusing. People will say, you know, why isn't it inclusive? How come it doesn't include the element at the end? Well, there's a lot of reasons for that. One is that it makes empty ranges natural. If you have, say, an iterator here and, if you have an empty vector, a vector that contains nothing, its begin and end are the same iterator. And because it's inclusive-exclusive, because we're excluding the end iterator, it means I have no elements. That's very natural. If you work with inclusive-inclusive ranges, then there's no natural way to represent an empty range. The other reason why this is great is this exactly imitates how built-in arrays work. If you look at array, let's go back to that array of 5. So if I say int r5 is stuff, I can talk about, because I've got an array here in memory, 22, 33, 44, 55. If I say address array of 0, that's this element, the first element of the array. If I say address array of 0 plus 5, which is the size of the array, I get a pointer to 1 past the end of the array. C++ and C allow me to talk about the address of this element, but I cannot dereference such a pointer. And if I'm iterating through this array, if I say for for size ti equals 0, I less than 5, plus plus I, what I'm doing is I'm saying I want to start at 0 and I want to go as long as I'm less than but not equal to the size of the array. I can use indices, the size t with vector, and I can also use iterators, which are an imitation of pointers, in exactly the same way. I want to start at the first element and go up to, but not including the end. So vector really is imitating arrays strongly. This inclusive exclusive thing is not some crazy thing that fell out of the sky someday. It's simply imitating arrays, which you've used since you began programming C++. But it can be somewhat unintuitive when you first see it. Now, if you look at this loop, I don't need to worry about that. I'm just looking at for vector int iterator I equals vBegin. Well, I'm starting at the beginning. As long as I not equal vEnd, and then I increment I, this loop says what it does. It's very natural. Now, beginning in Visual Studio 2010, I don't have to write this long-winded thing. I can simply say, I can delete this and say auto. This is a new feature from C++ OX, and it's a very simple feature. All that it says is make the type of this variable, in this case I, the same as the type of whatever its initializer is returning. The compiler knows that the type of vBegin is a vector int iterator because it was declared that way in the vector header. In fact, if I hover over what this is, there's a bunch of template stuff in here that makes it a little more verbose, but it's showing that vBegin really does return a vector iterator. So just by saying auto here, I say, hey compiler, make the type I the type of this other thing. You know what that other thing is. I don't need to go write it out. So you can see this loop is much shorter, and it's easier to write. So that's one of the ways that C++ OX makes this sort of thing more convenient. So that's iterating over elements, begin, end. I've written this loop in a certain way. I've used not equal instead of less than, and I've used pre-increment for reasons that have to do with other STL containers and efficiency. In particular, if I look at a vector int iterator, it could be a raw pointer. That's actually possible, or it could be a class type. So what iterators are is that they're a generalization of pointers. Again, it's using operator overloading to imitate a pointer. So if I have a vector int iterator, like this, some iterator I, and I've got a vector somewhere, I don't know what it is. This iterator points to a particular element of that vector. It can be dereferenced, it can be incremented, it can be decremented, I can add some index to it, I can even use brackets like I can with a pointer to get a relative index, exactly what I can do with a pointer. Iterators are a generalization of pointers, and this is how the STL breaks that dependency between containers and algorithms by saying, okay, every container is going to come with its own iterator. Vectors have vector iterators that act like pointers. Lists have list iterators that act like pointers with restricted abilities. So if I use a std list, std is how I pronounce the standard namespace, what it is it's a doubly linked list. Every programmer has seen one of these before. And if I get a list iterator, it'll point to an element. Now if I want to go to the next element, if I was using a handwritten C container, I would need to say something like p equals p arrow next, or p equals p arrow prev to get to the previous element. That's how to get to the next element. Whereas if I have a raw pointer, what I do is I say, plus plus p to get to the next element. If you look at what STL iterators do, is they abstract away the different implementations of containers, and if you have an iterator getting to the next element, is as simple as following the model for a pointer and simply saying plus plus I. So if I have a std list iterator and I say plus plus I, this is an overloaded operator call. What it's doing is it's calling this member function. It's a totally normal member function called operator plus plus. It just has a kind of funny name, and the core language has a way to call it in a more convenient way. And what that does is internally, this std list iterator contains a pointer, and it's simply going to say p equals p arrow next, whatever the name of this internal next data member is. It's not actually called lowercase next like that. So if I have a std list here, I would be able to use the same loop. I would just need to rename v to l, and I would be able to loop over every element of my doubly linked list in the exact same way that I would loop over a vector or a built-in array. This is enormously powerful. It allows you and algorithms to ignore the actual implementation of a container and even its structure and only focus on what it cares about, which is getting to the next element, getting to the previous element, that sort of thing. So I mentioned algorithms. Let's take a look at one of those. I can include the algorithm header like this. STL headers have no extensions. One of their historical things, there was a debate about what extension to give the new headers when the STL was added. They couldn't come to an agreement, so they said, hey, why don't we just get rid of the extension at all? We don't need it. So that's why STL headers have no extensions. So if I include the algorithm header, now I can use algorithms from the standard library. So say I've got a vector, and I'm going to push back some random numbers into it. Say I'm going to push back a 55, a 33, a 22, 44, and then an 11. Oh, I got some autocomplete there. That was nice. And then I can loop through my vector and print out every element. We've seen this before. What if I want to sort this vector? Well, the algorithm header has a function for that, and it's called sort. It's std sort, but I have said using namespace standard. That's the other thing that will often trip up programmers who are very new to using the standard library. All of its components are put into a namespace called std, the standard namespace, in order to not conflict with other namespaces. This prevents the old C trick of having to decorate your function names with the name of the library and then an underscore and then the actual name of the function or class or whatever it is. The standard library doesn't need to resort to that because it has namespaces. And in source files, if you simply use what's called a using directive, using namespace std, then you can refer to elements of the standard library without saying, here's what you would have to say without that. You'd have to say std : all the time. Now, it's very evil to put using directives in headers because that will go pollute whoever's including that header. So in headers, you'll have to see std : vector all over the place. But in a source file, it's totally OK to use a using directive. That's what I've done here because it's a pain to type all the time. So if I call sort, and I have included the algorithm header, I can say I want to sort all of this vector. So I say sort vbegin vend. And I can compile this, run it. Even though I push back 55, 33, 22, 44, and 11, when I'm done, the vector's printed out in sorted order. Here you can see one of the things that I've actually worked on because I put a breakpoint before the program exited. If you look at the locals or the watch window, and this would be in Visual Studio 2005 or higher, which I hope you're using because this has been the latest feature for the last 5 years. If I look at the vector in the local or watch window, I can see that this vector, v, I'll move this over, which is of type, this font may be a little hard to read, std vector int, the vector is displayed as having 5 elements whose values are 11, 22, 33, 44, and 55. Even though the vector contains a bunch of raw pointers and is doing a lot of pointer arithmetic, this visualizer in the IDE shows you conceptually what the vector is. It's got 5 elements. Here are their values. You don't need to worry about that. They're stored with pointers and all that sort of thing. So I could look at that without looking at the output of the program. So what sort is it's a function template that's templated on iterators. It can sort STL containers that, as long as they're random access iterators, and vector is a random access container because I can access the nth element of it, std list is not. Because it's a doubly linked list, I can't ask a std list, hey, give me your 5th element in constant time. It doesn't know where the 5th element is. It would need to follow these pointer links to get to the 5th element. So if I try to call sort with a list iterator, what will happen is I will get a horrible template error. This is maybe the most major weakness of the STL, and currently it's unavoidable. The fact that when it explodes at compile time, you'll get exhaustive errors that can be dozens, sometimes even hundreds of lines long that refer to details of the standard namespace, the implementation stuff that you don't need to know about. And this is because when this sort template is instantiated, it is going to refer to, you can imagine that somewhere in the implementation of sort, there's the expression, I've got some iterator and I need to go access the nth element. So you could see I plus n and this is being stored somewhere. Maybe it's I minus n, that sort of thing. This expression is not valid for std list iterator, but the compiler doesn't know that until it actually goes and instantiates the guts of sort. So when it explodes at compile time, the error will be somewhat hard to understand. As you get more experience with the STL, you can learn to interpret those template errors pretty rapidly. It never hurts to go ask the most experienced developer on your team, hey, what's going on with this error? But if you are the most experienced developer on your team with the STL, and you haven't seen these sorts of errors before, it can be a little intimidating at first. C++OX feature called Concepts was hoped to make these sort of errors easier to understand. Unfortunately, concepts had to be removed from C++OX, so we don't have nicer errors in Visual Studio 2010. In future versions, we'll be looking at what we can do to sort of relieve some of the complexity of template errors, but it is a hard problem. Fortunately, the great thing about compile time errors is that you see them on your machine, a developer machine, instead of allowing users to run into runtime errors. The STL loves pushing problems to compile time. It does not like deferring problems to be detected until runtime. So it's another way that the STL helps both with performance and correctness of your programs. So here I'm showing how to sort a vector, but because the sort algorithm is templated on iterator type, it can work with anything that's a random access iterator. And in fact, raw pointers, just an int star, is a random access iterator. So if I had, this is one of the ways that the STL can work with plain old C code, if I have an int array with 5 elements that's initialized to 55, 33, 22, 11, 44, I can say sort, and here I'm going to show you exactly how I get these pointers. Int star begin is address array 0. I could also simply say equals ARR and get a decay from array into pointer, one of those somewhat arcane things to see. And then I can say int pointer end is address array 0 plus 5. Here I could use count of or one of those templates that allows you to figure out, or a macro, macros are somewhat evil, figure out exactly how long the array is, but I'll just put a hard-coded 5 here. You'll notice I'm not writing address array of 5 because that technically triggers undefined behavior. If I tried to write address ARR of 5, the compiler is free to do whatever it wants with this, include crash the program, because there is no 5th element, even though I take its address immediately. So I'm not going to write that. Instead, I'm going to get the 0th element and get a pointer to that, and then increment that by 5, and I can talk about that address even though I can't get at that element. Then I can say sort from begin to end. And then I can go print out my array for size ti is 0. Actually, I can just use those pointers. For int pointer p is begin, as long as p is not equal to end. Again, I could write less than here because it's a pointer, but I'll say that. And I can increment p and then see how difference be. You'll notice that when I change this loop to work on a raw array instead of a pointer, I didn't really have to modify it that much. In fact, I could have even said auto here, and it wouldn't have changed at all, except for the fact that I said begin and end here instead of v.begin and v.end. So if I actually execute this, save, oh, there's no more vector. I'll put a statement here so I can break. R of 0 is 0. Breakpoint. Goodbye breakpoint. Save, execute. And build succeeded. If I look at what this did, I'm now sorting a built-in C array with the standard sort function, and I print out the sorted elements, 11, 22, 33, 44, 55. And if I went and looked at the locals window, I would see that, yes, I can even see that in the debugger. So the standard sort algorithm doesn't know, and this is the Orwellian way to put it would be ignorance is strength. Std sort is ignorant of what iterators it's working on. They could be raw pointers, they could be vector iterators, they could be dec iterators, they could be any random access container. It doesn't care what elements it's sorting. This could be a vector of int, it could be a vector of string, it could be a vector of vectors, a vector of your own class types, your own structs, whatever you like. And in fact, it doesn't even care how you're going to sort it. And so this is the way I had previously scribbled that function objects can be used to customize the behavior of the STL. So if I've got my vector, let's use a vector of string. This can be fun. So I'm going to go include the string header. It's always important to include exactly the headers that you need and to never depend on one STL header dragging in another. The standard says that they can include each other in unspecified ways, and we implementers can and will change the ways that the headers include each other. So if you just assume that the IOStream and OStream headers drag in std string, you will eventually be broken as we update the compiler and libraries. So in order to be able to seamlessly upgrade, it's very important to be able to include the headers that you actually need, rather than just assuming that they'll get dragged in. So if I have a vector of string v, I can push back a bunch of strings. I'll just push back a few. Push back cat, and then v, push back antelope, I want a long string, v, push back puppy, and v, push back, let's see, elephant. There we go. I can then sort, actually this is the same length. Let's try, what's a 4-letter animal? Dog. No, dog's too big. Bear. There we go. Thank you, Charles. Okay, so if I sort my vector, v.begin, paren, v.end, paren, I can then print out the element for auto I is vbegin. Now in C++ OX, there is a new for loop that will allow me to write something even shorter here, but it's not yet implemented in Visual Studio 2010. There's a non-standard extension that I'm not showing here because it has gotchas. It's really good to either use this for loop or use the standard for each algorithm, which are both perfectly efficient. ++I can print out that ith element. So if I sort strings, by default when I compare strings, they're compared lexicographically, which is a fancy way of saying that they're compared in dictionary order. So strings that begin with letters like A will be sorted before strings that begin with letters like C. So if I sort this, stop. Let me compile it from scratch. Why am I getting a build error? Oh, because I've got this array down here. Oops. Nuke. And goodbye vclear. Put a breakpoint here. Okay. Compile. So if I look at the output of this sorted vector, they'll have been sorted in dictionary order. So I get antelope, bear, cat, puppy. A comes before B, comes before C, comes before P. But what if I decide that I actually want to sort it in reverse order? Well, I can use a standard library function object, which lives in the header functional. Include functional. And I can tell sort, okay, you're sorting a vector of string. I actually want you to sort it the other way around. So if I say greater string, this is a type. It's a struct that has been templated on an element type, and I want to construct I want to default construct a temporary of that type. So if I put some parentheses there, I just get an object of that type. I could go give it a name, but the usual practice is to just make it temporary. I can then customize how that sort works. So if I execute this, what will happen is that I will get this vector of string in reverse order. And I get printed out puppy, cat, bear, antelope. Now the antelope, which starts with A, is being sorted at the bottom. So the way that sort works is that, say I'm sorting a vector of int. What's happening is that by default it uses the less than comparator. So if I have a bunch of ints, 11 is less than 22, is less than 33, and so forth. Of course, if there's equal elements here, they'll all be packed together. So if I have duplicates, I would get 22, 33, and so forth. So if I use greater, what that is doing, it's reversing the sense of the sort. Now the biggest element will come first. For a string, by default, biggest means the one that occurs last in the dictionary. But I'm not restricted to just using the function objects that the standard library gives me. I can use my own function objects. And in Visual Studio 2010, there's a new C++ OX feature called lambda expressions that allows you to define unnamed function objects very easily. Its syntax is a little intimidating at first because it's got brackets in new places, but it's actually extremely convenient to use. So, for example, here I've got a bunch of strings. What if I don't want to sort them on dictionary order? What if, for whatever reason in my program, I need to sort them by length? So I want the shorter strings, like cat, to occur first, and the longest strings, like antelope, to occur last. I can do that with a lambda. I could also do it with a handwritten function object if I was using Visual Studio 2008 or earlier. And sometimes you actually do have to resort to handwritten function objects if you're doing very advanced things. But lambdas are a very convenient way to define function objects exactly where you need them. So the syntax for writing a lambda is empty square brackets. This says, I'm a lambda that captures nothing. It means it doesn't contain any state. And then it will take, because it's a function object, two strings. So it's going to take a const string reference left and a const string reference right. Of course, I want to take these strings by const reference because I don't want to go copy them. And I'm going to insert some indentation here. And then I put a brace here. And now I can write a function body in line as if I were writing the function outside of main itself. And then I can say simply return. Now, this is a lambda. It needs to return whether the left string is less than, in some sense, than the right. And I said I wanted to compare their sizes. So I want to say return whether the left string size is less than, this is just comparing two sizes, the right string size. And then I put a brace to close my lambda. And then I have a paren semicolon that closes the sort. And I can tab this a little bit. There we go. If I wanted to be really exhaustive, I could show how they match up here, but I like to compress that down a little. So now this function object here is saying when you compare two strings, a string on the left and a string on the right, I want you to use this comparing their size instead. So by providing a function object to the STL, it doesn't care what container it's sorting as long as it's random access. It doesn't care what element it is, could be int string. It doesn't even care how it's being sorted. It just needs some way to compare two elements. And this function object, or functor, or specifically a comparator, tells the STL what to do. If you're old school C programmer, you can think of this as a callback. The STL is calling back your code, but the STL terminology is that this is a function object, meaning it's a struct or a class that overloads the operator paren member function. So if I compile and execute this, build started, succeeded, you'll see that it's actually printing out cat, bear, puppy, antelope. So it's ignoring the dictionary order of the strings, and now it's simply comparing their lengths. Now if you go look at the specification of std sort, one of the important questions you might ask is what happens when elements compare equal? In that case, what sort will do is it will sort them in unspecified order. That's standardese for saying it's got to do something. It can't go like crash a program. That would be horrible. But you're not guaranteed as to the relative order of equal elements. So if I had elements here, this is why I was trying to avoid it earlier. If I had dog in here and kitty and other strings that were identical length, std sort would not guarantee me what order they would come out in. They could come out in the original order that they were in the vector. They could come out reversed. They could come out randomly permuted if I had more than two, just because the sort algorithm would need to spend more time to preserve that order. Now, if I wanted to request specifically, hey, STL, I want to sort them on their sizes, but it's vitally important to me that if cat occurred before dog, then you need to preserve that fact in the final sorted sequence, no matter where those elements go. I can use another STL algorithm, and this one naturally is called stable sort. This uses a different algorithm that will preserve stability, which is the CS term for preserving the order of equal elements that are equal when viewed through this particular comparator. The reason why that's not the default is because the stable sort algorithm may be less efficient. It has to do a little more work to make sure it's not going to mess up that ordering. And that's why if you just call sort, it's going to say, I'll sort them in the equal elements in unspecified order because I want to be fast. If it were possible to guarantee stability for free, then the STL would have done that. So you can look up all of the algorithms in the STL in your favorite reference book. You can look them up in MSDN. I myself go directly to the standard. The draft for the C++ OX standard, which is not yet completed, but it's entered the final committee draft phase, is available on the web. You can search for it, find it pretty easily at the Standardization Committee's website. I would show you, except that today, for some reason, the website is inaccessible. If you look at the standard, it can be intimidating to read. I certainly wouldn't recommend every programmer to look at it. You should just go to like MSDN or a book. I myself go directly to the standard because I can browse it very rapidly, and it's guaranteed to be authoritative. If there's a bug in the standard, then every resource that's derived from the standard will have that issue as well. So I can look at the algorithms library, and if I just want a list of the algorithms, reading this is actually very simple. I can look at mutating operations or sorting and related. Hey, I care about sorting, so I could look here, and it will show declarations of various functions like sort, and then I can scroll down and I can see stable sort. If I only care about signatures, this is very easy to read. I don't need to know how to read standardese in order to see, oh, it's a template, blah, 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 and it's called stable sort. Effects, it sorts the elements in the range first last, and then it talks about the complexity. It has this remarks. This is where parsing the standardese could be a little more advanced. If you're not familiar with the term stable, you could look it up in Wikipedia. That's a great thing. But overall, the specification of the standard library is pretty approachable. If you go look at the upper parts that refer to the core language, that's very advanced to understand. But I look at the standard library, and it basically tells me what all of these algorithms are doing. As I mentioned, the STL has over 100 algorithms. A dozen or a couple dozen were added in C++ OX in Visual Studio 2010, from basics like copyif to more advanced things like isSorted, partition copy, that sort of thing. If you want to do something that is pure computation, general computation, chances are there's an STL algorithm for it. If not the default behavior, then it should be customizable. Many things that you might not expect would be implementable by a standard algorithm actually are if you use the right function object with them. The reason why to use STL algorithms, sort is pretty obvious that I want to use a sort function because writing one of those requires a lot of work, easy to get wrong, easy to get non-performant, like a bubble sort that's quadratic complexity. Std sort is implemented with an intro sort, which is like a quick sort, but it doesn't suffer from the quadratic complexity worst case behavior. But for something like a transformation or a copy or remove, you might say, hey, why can't I write this by hand? Well, the answer is that if you use an STL algorithm, you're guaranteed that you're not going to make off by one errors. If you just pass begin and end, the STL will get all of that right for you. You're guaranteed that if the implementers have a more efficient implementation, they'll use that one. They can do things like remove checking from iterators. They can unwrap iterators to raw pointers and do more things. In fact, this is one of the many optimizations in our implementation of the standard library. If you have something like a vector of int, if you look at what copy is specified to do, it copies one element from the source into the destination and essentially does a loop. But for things like integers and chars and long, these things are of built-in type. It's actually more efficient to call a memmove and things like that on them. The STL, because it is powered by advanced template machinery, can actually detect at compile time when a vector is of type has elements of type int and can resort to calling memmove and other library functions like that rather than loops, which might not be as efficient. Over time, we'll add more optimizations like that. We're always looking for opportunities to do that. But we've already got them in 2005, 2008, and especially 2010. The STL also uses the C++ OX feature R-value references, which makes containers of standard library types like strings and other vectors and your own types, if you write your own move constructors and move assignment operators, more efficient. It removes unnecessary copying. So that's sort of a quick overview of how to get started with a vector. and STL algorithms. As I mentioned, the STL contains many containers. This is just part one of a series. I didn't get into the other sequence containers. I'd mentioned std list, which is a doubly linked list. There's DEC, which is a doubly ended queue. That is not often useful, but when you need it, is very valuable. There are also the other stars of the STL, the associative containers. Other languages will call these dictionaries. Hash tables are kind of associative container. The STL has sets and maps and multi-maps and now unordered maps, which are hash tables, in C++ OX and Visual Studio 2010. These are ways to write other algorithms that look up keys and find values or store a sorted set or an unordered set of items, and you can traverse them and use them with other STL algorithms. The opportunities to use these in your programs are almost unlimited. You can write so many things just by using vector and map and algorithms like sort and replace and transform. I've only scratched the surface. In future parts, I'd like to go into more detail. So if you'd like to see something, request it in the comments. I'll see what I can do. So that's all that I really have. See you next time.